Good evening and welcome to Chapter 6 Notes on Chemical Bonding. In today's section, we are going to be looking at building molecules. So when we build them, we have to look at the bonding and the different types of bonding that occur, how we're going to determine what type of bonding occurs, and then we're going to focus in on covalent bonds. And we're going to begin to look at how molecules actually put together covalent bonds. So we will begin with the types of chemical bonds. The first type is a covalent bond. Covalent bonds are broken into two types itself. We can have nonpolar covalent bonds, in which we will have equal sharing of electrons, and polar covalent bonds, in which we will have an unequal sharing of electrons. And how electrons are pooled all depends on their electronegativity. And we were introduced to that at the end of Chapter 5. The other type of bond we can have is an ionic bond. In ionic bonds, we no longer share electrons, but we have a complete transfer of those electrons. So let's look more closely at the types of bonds. For a nonpolar bond, we just said that it will have an equal pool of electrons between the atoms. This means its ionic character, or how close it is to an ionic bond, is going to be less than 4%. How we determine this is we look up their electronegativity differences. We're going to take the larger minus the smaller, and we're going to see that they have very similar electronegativities because their difference between the two are going to be less than 0.4. Polar bonds. Remember, this is unequal sharing of electrons. So the element that is more electronegative is going to have a greater pull on the electrons. Because it has a greater pull, the electrons will kind of hang out more near that element. So it does cause some slight ionic character. So this is anywhere from 4% to 51%. We also will give these weird little symbols, which just mean partial. The more electronegative element gets a partial negative charge. It's not completely negative, but because it has more pull on the electrons, it's going to seem more negative. So we have a partial negative charge. Our less electronegative element gets a partial positive charge. So it's got more, or it loses its electrons, so it's got that greater pull from the protons. So it's left with a partial positive charge. So to find out if you have a polar molecule, again, looking at your electronegativity differences, they're going to be somewhere between 0.4 and 1.7. And finally, we have ionic. So this is an electrical attraction between cations and anions. So there has been a complete transfer of electrons. When it transfers its electron, one has completely gained the electron, making it negative, and one has completely lost their electron, making it positive. So you have the anion and the cation that are then going to come together because of their charge. And these elements are going to have electronegativity differences that are much greater than 1.7. So let's look at predicting the types of bonds you would have. So you're going to need your bright orange sheet. So why don't you pause it and go find your bright orange sheet. So if you're looking at your bright orange sheet, you're going to look at the side with the periodic table, and you're going to look up the two elements listed. So if we look, H has an electronegativity value of 2.1. S has an electronegativity value of 2.5. So we're going to subtract the 2, so we're going to take 2.5 minus 2.1, and we get a value of 0.4. This is going to make this then polar. For Na and Br, we look up Na. Na gives us a value of 0.9. Br gives us a value of 2.8. So we take 2.8 minus 0.9, and we get 1.9 which means we have an ionic bond. For Cl and O, Cl has an electronegativity value of 3.0. Oxygen has an electronegativity value of 3.5. So 3.5 minus 3.0 gives us 0.5. So again, we are a polar covalent bond. And Br and Cl, Br is 2.8, Cl is 3.0. So 3.0 minus 2.8 gives us 0.2, which means we have a nonpolar covalent bond. So when we just make those bonds, those covalent bonds, we are going to form molecules. So molecules are just a neutral group of atoms held together by covalent bonds. A molecular compound then is going to take different molecules and put the molecules together so that we have a much larger compound. And usually we don't draw the structure for everything, but we use a molecular formula to tell us all of the different molecules that are being joined together. So this contains the number and the types of atoms present in a molecular compound. What it does not include then, of course, is the type of bonding, or what elements are technically bonded to other elements. So characteristics of covalent bonds. What we could look at is the bond length. So this is the average distance between two bonded atoms with minimum potential energy. We're going to find that the bonds are constantly moving, or the atoms are constantly moving, so this bond length is constantly growing and shrinking and growing and shrinking. So we take the average distance that has the lowest energy. When we talk about bond energy, it's just the energy that would be required to break that bond. So the further away or how close it is to each other, they're going to have different energies. So that's why we always look at what would be the smallest energy. What would it need to break that bond? And both of them will vary with the type of atoms that combine, and if there are other atoms that may be already bonded to one of the atoms. And that's all because of how many electrons are already there, or that each atom brings to this bond. So when we start looking at bonding, we know that compounds will gain, lose, or share electrons, but they will share them in such a way that they follow the octet rule, and that is that it has 8 electrons in its highest occupied s and p orbitals. So octet, 8, and again we're going to look at highest occupied s and p. So which elements have full s and p? Those are the noble gases. So again, we are going to gain, lose, and share so that everything feels like a noble gas. However, there are some exceptions. And the first one is hydrogen. Hydrogen's only got 1 electron, so once it forms one bond, it's happy. It's not going to form any other bonds. It's going to stick with 2 and no more. Exception number 2 is boron. For whatever reason, boron likes to be happy with only 6 electrons. So it does not need to have 8. If it forms a bond and it has 6, it is going to be happy. Or some elements may have more than 8 if they are paired with F, O, and Cl, which are our highly electronegative elements. Because of this, those elements will pull on the electrons so much that the element that's left over will feel like it doesn't have those electrons. So it is going to look for more or other elements out there that have those electrons. So it may make more or have more than 8 electrons around it. And the fourth exception is any expanded valence. and this is bonding within that D block. So let's look at how bonding actually works. So how we share electrons and where we share electrons. And we can do this using orbital notation. We're going to look at each element individually. So if we're looking at HCl, we know that H has an S, and that's it, and it's got 1 electron. Cl is S and P. Now we're just going to look at the highest or the outermost electrons. So these are going to be the ones that are just in the S and P orbitals. So we're not going to worry about what we have in D. We're not going to worry about what we have in F. We're just going to look at the S and P. Cl has both of its S filled, but then it only has 7 in the P block. So it's going to have 1 space left over. Well, conveniently enough, H also has 1 space left over. So what happens is basically this H is going to share there, and that P is going to share there. So they're going to share basically these electrons, and then this area, they will form a bond. So they will form a bond so that both of those empty orbitals are now full. If we look at F2, so we have F, it's got its S, or I guess it's not 1S, we'll just look at S, and then we have the other F, which has S, and of course their S is full because they are in the halogen group. And then we have the P's, and the P's are 7, just like chlorine. So it's going to share in this area. So this one comes down and shares, this one goes up and shares, and again it makes a bond. So HCl would have 1 bond, F would have 1 bond, because it only needs to share 1 electron. So let's look at some that are a little bit more. For example, N2. If we look at N, it has its S full, and now we look at the P, and it is 3 over in P. So we have 1, 2, 3, again filling according to Hund's rule. So it's got 3 electrons it can still take in. It's got room for 3 more. So it's going to share here and make a bond. It's going to share here and make a bond. And it's going to share here because each of these orbitals has 1 electron it can share. And then we have H2O. So now we got 3 things lining up. So we have H, O, and then we have 1 more H. So we've got our S, in which we only have 1 for each of the H's. And then we have O has a full S, and in its P, it is 4 over. So 1, 2, 3, 4. So it can share with this H here and make a bond. And it can share with this H here and also make a bond. So we've got 1 bond and 2 bonds. So orbital notation is just one way of showing you how to make those bonds. Another way we're going to look at is using electron dot notation. It also only shows the valence electrons, which means only the S and P. In this time, instead of using arrows, we're just going to use dots to show electrons. Our number of dots is going to be determined by the group number. Well, now you say we can only have an octet. Those in the P block start at group 13, group 14, group 15. So what we're going to do is we're going to subtract 10 from that group number. So we're going to take out those D elements and not count those electrons. So if we were looking at just the S and P and we were going to assign group numbers, we're going to have group 1, group 2, group 3, because we're going to minus 10, group 4, 5, 6, 7, and 8. So that's going to tell me how many electrons we have in the valence shell. So if we wanted to do some simple dot notation or find out how many dots are around these elements, instead of drawing out the orbital diagram, we're just going to use dots and we're going to place dots around it. So what we're going to do is find the element on the periodic table and start placing the correct number of dots based on its group number. So we look up P. P is here. It is in group 15, which remember is going to mean it has 5 electrons. Because it's in the P block, we subtract 10. So we are going to put dots around. Now, when we think about this, we think about it as a box. And we are going to place dots, one on each side of the box, and then double up. Another thing about placing them is that we want them as far apart as possible, because what do we know about electrons that have the same charge? They're going to repel. So we have 1, 2, 3, 4, and then we're going to double one of them up and have 5 dots around phosphorus. So let's look at Cl. Cl is in group 17, so it means we have 7 dots. So we're going to go 1, 2, 3, 4, 5, 6, 7. Sr is in group 2, so it only has 2 dots. So 1, 2, and Xe has all 8 because it's a noble gas. So 1, 2, 3, 4, 5, 6, 7, 8. Now what this tells us is anything that is empty again, it is free to bond in. So P would have 3 electrons it could share or that it would want to share. Cl has 1, Sr has 2 because it doesn't have anything here, and then Xe probably won't do any because they're all full. So it's another way of seeing how many bonds could this element make. In our next video then, we will look at building molecules based on these dot notations. Have a good night.